In this video, we present our research on 3D human pose estimation and provide several examples. Our work is motivated by the challenges of existing works that show limited generalization to out-of-distribution data and need extra steps to scale with many cameras and uncommon camera setups. To address these challenges, we present UPose3D, a 3D human body keypoints estimation method from multi-view videos with great scalability to a large number of cameras and generalizability to out-of-distribution data. Additionally, unlike others, we do not rely on 3D annotated data and train our model using motion capture data to improve its generalizability. Our solution starts with 2D pose estimation. Here, two camera views are demonstrated on the left, which are passed to a pose estimation block to obtain 2D keypoints and their uncertainties. Next, we use our proposed cross-view projection strategy to map the predictions from all camera views onto a reference view. Here, we visualize our cross-view projection strategy using typical two-view predictions. To find the projection of the left view on the right one, we first find the epipalar line and then select the closest point for the reference view. As seen on the right, repeating this process for all views gives each joint a point cloud. The obtained point clouds are then passed to our proposed pose compiler for additional processing. Like the 2D pose estimator, our pose compiler outputs a set of keypoints and uncertainties. Finally, we combine the output from our pose compiler and 2D pose estimator to perform maximum likelihood estimation to find the 3D keypoints. In this example, we illustrate 2D keypoint distributions as heat maps. However, unlike traditional heat maps, these distributions are differentiable, and the output resolution or image truncation does not cause any limitations. The likelihood loss function is formulated as the negative log of the likelihood of a 3D point reprojected to all views, which is shown as U in the center. In every refinement step, we project this point onto every view, calculate the likelihood given the predicted keypoint distributions, and update the 3D point using the obtained gradients. In practice, we estimate the second-order derivative using the LBFGS optimizer to speed up the 3D triangulation and repeat this process until the changes in 3D space reach a certain threshold. In our proposed pipeline, we design our solution to not require any form of 3D supervision. Therefore, we train the 2D pose estimator on any widely available 2D image dataset. We also propose a synthetic training strategy for our pose compiler since it only requires 2D inputs and outputs. We start by randomly placing cameras in a randomly selected volume to simulate a multi-view setup. We ensure that each camera looks roughly at the center while maintaining a correct up direction. Next, we take a motion capture sequence and extract 3D keypoints. These 3D keypoints are projected onto each camera view to form the 2D ground truth. In the following steps, we heavily corrupt the data and apply our cross-view projection strategy to obtain the input point clouds for training the pose compiler. Here are some examples of our method compared to the state-of-the-art in an in-distribution setting. We train all elements of our model on the target dataset and show that it performs competitively with the state-of-the-art. Despite some jitters, our model is more robust and does not produce large noises. Here are some examples of input and outputs of our proposed method compared to one of the best-performing triangulation approaches. We perform this experiment in an out-of-distribution setting, meaning we do not train any network element on the target dataset. Despite this, our method has fewer noisy artifacts. It can even predict hand joints with high accuracy. We also examine the scalability of our pipeline with additional camera views in 2 out-of-distribution evaluation schemes. The error of our method consistently decreases as we add more cameras, meaning our model scales, unlike traditional methods. Finally, we test the scalability of our approach with up to 107 cameras and show that the error decreases while the runtime remains constant. In conclusion, we introduce an uncertainty-aware solution for 3D human pose estimation that does not require 3D annotations. Our method scales well with additional camera views and shows robust results. This is evident by its ability to achieve state-of-the-art results on unseen data while performing competitively with the prior works of the last few years in distribution experiments. Thank you for your time and attention.